Hello, welcome to our channel, and in this episode I'm discussing spectrum and how spectrum is associated with the drawback of Bohr's atomic model. So let's meet on the other side to understand what is spectrum and how it resulted into the drawback of Bohr's atomic model. Welcome back. So let's see what is spectrum. So spectrum is splitting up of a radiation into its components. Say this is a prism, and if I make white light incident on this prism through a slit, and when the white light crosses this prism, it would split up into 7 different colors like this. So it would be violet, indigo, blue, green, yellow, orange, red. So this is termed as spectrum of white light. So when white light is splitting up into 7 colors, because it is made up of 7 colors, that's why it is splitting up into 7 colors. So this would be considered as the spectrum of white light. So just to sum up, on your screen you can see the definition of spectrum and how spectrum is observed when light is passed through the prism. You can jot it down or you can take a snapshot. How spectrum is further classified. Now spectrum is further classified into 2 different types. The first would be absorption spectrum and second would be emission spectrum. So there are 2 types of spectrums, absorption spectrum and emission spectrum. So let's try to understand what is absorption spectrum. Now absorption spectrum would be, the word absorption itself explains what would be the meaning, because absorption is, suppose when we intake food, the food gets absorbed in our intestine. That is, a part of it, the nutrients which are required for the body are absorbed and rest is excreted out. So in the same way, absorption spectrum would be when a light is made incident on a solution, a part of it would be absorbed and part of it would be transmitted. So that is absorption spectrum. Now to understand it with a very simple example, suppose this is a beaker and I am creating, say, copper sulfate solution. So now copper sulfate solution is blue in color. So it would be, the solution would be blue in color. Now when white light is made incident on this solution, we will see that the solution is blue in color. So this is absorption spectrum, because the white light which is falling, part of it is absorbed and only blue color is reflected back, and which is visible. Now if you just change the situation, if you place this beaker in a dark room where no light source is there, and then if you try to see the color of this solution, you will not be able to see the color. This is because light is not falling on this solution, and so color is not visible. So it is always comparison between the incident and the transmitted radiation. Now let's try to understand the absorption spectrum with an experiment. Now say this is a light source and a slit is placed in front of the light source, and Here I am placing a beaker in which a copper sulfate solution is placed, and the light which is coming from the slit is made incident on this copper sulfate solution, and the solution and the light which is coming out from this copper sulfate solution is passed through a slit and is made incident on a prism. So now the light which is falling on this prism would now be splitted into its components. Now the light coming from this slit is directly made incident on the prism. So if it is made on the incident on the prism, this light would basically split up into its components, and because this is white light, so it would split up into 7 colors, isn't it? We have just seen that if white light is made incident on the prism, it would split up into 7 colors. It would be violet, indigo, blue, green, yellow, orange and red, and this would be only blue color. The light which is coming out from the copper sulfate solution would be blue in color, so it would not further split up. But the light which is coming from the source would split up into 7 colors. So the comparison of these two spectrum is the absorption spectrum. That is, the copper sulfate solution is absorbing all the available lights, that is violet, indigo, green, yellow, orange, red. All lights are absorbed and only blue is transmitted out. Suppose if I change this solution by ferrous sulfate solution, now ferrous sulfate solution would be green in color. So now the emergent light which is coming out from this solution would be only splitting up into green color, because now green color is only transmitted. And likewise, if I create a solution of say cobalt nitrate, it would be red in color. So if the light is made incident, then the red light would be coming as a transmitted radiation, and it would be showing only red after the prism. So this is how we can compare the absorption spectrum, that this is the original light and this is the light which is coming out from the solution. So just summing up what we have done, on your screen you can see the definition of absorption spectrum and how we can compare the absorption spectrum with the incident radiation. You can jot it down or you can take a snapshot. So emission spectrum is when an element or a compound is heated or placed under the influence of electrical field, it would emit out some radiation, and spectrum of that radiation is emission spectrum. Now a very simple example is, in your class 11th you will do salt analysis, and in salt analysis you do flame test. So now the flame test is a characteristic example of emission spectrum. Now when we heat sodium or salt of sodium, it can be sodium chloride, it can be sodium nitrate. So when we heat a sodium salt, it would give golden yellow color flame. Golden yellow color that is emitted out, if it is passed through a prism, it would give a spectrum, and that spectrum would be termed as emission spectrum. So let's sum up. On your screen you can see the definition of emission spectrum and the characteristic flames of different metals. You can jot it down or you can take a snapshot. Up to now we have seen the definitions of absorption spectrum and emission spectrum. Now these absorptions and emission spectrums can have further continuous spectrum, and discrete or line spectrum. So let's try to understand what is a continuous spectrum. Now continuous spectrum would be when there is no boundary in between the colors, and the colors or the spectrum generally superimposes at the boundaries, then it would be termed as a continuous spectrum. Now I have given an example that if say white light is made incident on prism, so it would split up into 7 colors like this. So there are 7 colors. Now in these 7 colors you can't find the boundary. It would be violet, it would be starting with violet, then it would when indigo will become intense, we will see indigo color, then blue will become intense, we will see blue color, then green, yellow, orange and red. So all colors are basically present, and when they become intense they are clearly visible, but at the boundaries they superimpose on each other. So such a spectrum would be termed as continuous spectrum. That is, we can't differentiate between the colors and colors are superimposing at their boundaries. That is a continuous spectrum. So absorption spectrum is usually a continuous kind of spectrum. Say golden yellow color light is emitted out and this light is made incident on the prism through a slit, and if this light splits up into its components, then this spectrum observed would be termed as emission spectrum. So this was all about line spectrum and continuous spectrum. So summing up, on your screen you can see the difference between continuous spectrum and discrete or line spectrum and how they are obtained. You can jot it down or you can take a snapshot. In my last episode, I have discussed that Bohr gave a formula. Delta E change in energy is 2.18 into 10 raised to power minus 18 1 over n1 square minus 1 over n2 square. Now basically from this formula I have already discussed that we can calculate wavelength associated with it. So hc by lambda would be 2.18 into 10 raised to power minus 18 1 by n1 square minus 1 by n2 square, and if I place hc in the denominator, so it would be like 1 by lambda, which is nu bar or wave number. This is wave number, would be 2.18 into 10 raised to power minus 18 over 19.89 into 10 raised to power minus 26, which is the value of h into c, 1 over n1 square minus 1 over n2 square. Now if I change the values in centimeters and solve it, so it would be nu bar would be 109677 1 over n1 square minus 1 over n2 square in centimeter inverse. So wave number would be in centimeter inverse. So if we know the initial position of the electron and final position of the electron, and we can calculate the wave number that is associated with that electronic transition. So to sum up, on your screen you can see the formula for calculating the wave number and having Rydberg constant. You can jot it down or you can take a snapshot. Now let us try to understand what is line spectrum for hydrogen atom, and Bohr explained the line spectrum for hydrogen atom. Now according to Bohr, the energy levels or the quantized levels can be first energy level, then it can be second energy level, then it can be third, similarly fourth, fifth energy level and sixth energy level. Now he expected that only 6 energy levels are possible, and if you use the formula 2n square and sum up for all the energy levels or quantized states, it would contain more than 150 electrons. So he presumed that more than 150 electrons are not possible. So he expected that there are 6 possible energy levels, and now if electron is in the most excited state, that is in 6th energy level, Now there are different permutations and combinations by which an electron can fall back to the ground state energy level. Now the first permutation would be it can directly fall to the ground state energy level. The second permutation can be it can fall to only second energy level. The third can be it can fall to third energy level, or it can fall to fourth energy level, or it will be like only up to fifth energy level. Now I'm presuming that electron has come to the fifth energy level. Now from fifth energy level it can again fall to the ground state energy level, that is first energy level. It can fall to the second energy level, similarly to third energy level and fourth energy level. Now I am presuming that electron is now in fourth energy level. Now from fourth energy level it can fall to ground state energy level first or second or third energy level. Likewise from third it can fall to first or second, and from second it can fall to first energy level. Now these are the different permutation combinations by which the electron, when in hydrogen atom present in the most excited state, most excited state means the electron is in the hydrogen atom, it has not gone out of the hydrogen atom, and from that excited state it can fall back to the ground state energy level by 15 different permutation combinations. And these combinations were named like this is this series when electron is falling from any excited state to first energy level. Now here N1 would be 1 and N2 can be 2, 3, 4 and 2, 3, 4, 5. So this would be termed as Lyman series. Similarly, when electron is falling to second energy level from the excited state, so in this case N1 would be 2, N2 can be 3, 4, 5 and so on. So this would be termed as Balmer series. Now when electron is falling to the third energy state from any excited state, now N1 would be 3 in this case and N2 can be 4, 5 etc. It would be Paschen. Then this would be bracket and this is profund. So these are the series in which electron can fall. Now why we call it as a line spectrum? Now in this, say I am considering the first line in Lyman series. Now the first line in any series would be, for Lyman it would be N1 1 to N2, when from the lowest energy level to the next higher energy level, this is considered as first line of that series. So in case of Lyman it would be N1 would be 1 and N2 would be 2. In case of Balmer, the first line would be N1 would be 2 and N2 would be 3. So likewise we can calculate for the first line in each of the series. Now if I'm taking this first line, so in this first line if I substitute in the formula, say Hc by lambda would be 2.18 into 10 raised to power minus 18 into 1 over N1 square minus 1 over N2 square. Now this would give me a characteristic wavelength associated with this line. If I consider the second line, then it would also have a characteristic value. So likewise all the lines associated in each of the series are having a characteristic value that is associated with that line. So that's the reason it is termed as line spectrum. Now Bohr was able to explain the line spectrum for hydrogen atom. Now in hydrogen atom, just think that there is only one electron and one electron can fall back to ground state energy level with 15 different permutation combinations. So there are 15 different permutation combinations possible through which electron can fall to the ground state energy level. Just consider if there are more than one electrons, then the permutation combinations would increase in as a factorial value. And so this was the drawback of Bohr's atomic model, that Bohr was not able to explain line spectrum for multi-electron atoms. So just to sum up On your screen, you can see the line spectrum for hydrogen atom, and the drawback for Bohr's atomic model was he was not able to explain line spectrum for multi-electron atoms. You can jot it down or you can take a snapshot. This was all about the spectrum, its types, and drawback of Bohr atomic model. If you want to stay connected with us, then you can follow us on Facebook, Instagram, and Twitter. If you haven't subscribed our channel, then do consider subscribing to the channel, and while subscribing, don't forget to hit the bell icon to get instant notifications. As a student, it's always advisable to practice more and more questions, more assignments, more tests. And if you are looking for a destination where you can get more questions, more assignments, and more practice tests, then follow the link which is on the top of your screen, and it would serve your requirement to practice more and more. Thanks for watching the video.